Have you ever felt like modern computing is just hitting a physical brick wall? You're definitely not alone. So today in this explainer, we're diving into a totally radical blueprint that completely abandons traditional binary code in favor of extra-dimensional geometry and light. We are unpacking the self-state registration, or SSR architecture. It's a non-associative framework that sounds a lot like pure science fiction, but as we'll see, the math is incredibly real, and it changes absolutely everything about how we process data.
And because the math we're unpacking is frankly mind-bending, we've broken this beast down into 6 logical steps. We'll start with the von Neumann trap, see how we break traditional algebraic rules, tame the infinite loop, explore the p-adic fractal matrix, look at building actual computers with light, and finally scope out this zero-friction future.
Okay, part 1, the von Neumann trap, and specifically, the associative flaw. Let's get right into the fatal vulnerability at the absolute foundation of modern computers. Conventional computing logic relies completely on associative grouping. That basically means the order in which operations are grouped doesn't change the final outcome. Now sure, that predictability built our entire digital age, but it also guarantees linear periodicity, and that creates a massive structural vulnerability. I'm talking about the infinite feedback loop. Because standard math is so perfectly stable, a broken piece of code can literally just echo back and forth forever, eating up all your memory and completely freezing your system. It's the classic von Neumann bottlenecks.
So how do we fix it? Part 2, breaking traditional algebraic rules and entering the Octonions. To escape this trap, the SSR architecture forces a radical shift. Instead of executing chronologically, the data transitions to a path-dependent geometric state by literally breaking the standard rules of math. To gain this higher dimensional complexity, SSR systematically sacrifices standard algebraic properties. We're talking about expanding into an 8-dimensional Octonionic space, where we purposely throw out the associative law. In this kind of geometry, A times B times C is fundamentally different depending on exactly how you group them. The data becomes 100% context-dependent.
And comparing these number systems really proves why this matters. As you move from real numbers down through complex numbers and quaternions, all the way to AD octonions, you completely lose the guarantee of associativity. Because the order of operations in octonions no longer guarantees the same outcome, an infinite loop literally cannot sustain itself physically. When a loop tries to cycle, the shifting math causes it to just drift and break rank mid-flight. It destroys its own repetition. It's brilliant.
Which brings us to part 3, taming the infinite loop with geometric deflection. Because think about it, if a bad piece of code can't loop, it still has to go somewhere, right?
Well, when a logical contradiction happens, the system doesn't freeze or crash. Instead, that non-associative math forces an orthogonal shift. It basically deflects the chaos at a hard right angle, tossing it completely off the flat base space of healthy execution and up into this higher dimensional storage closet, a mathematical space called the Hitchin fibration. The air gets instantly insulated from your processor core, but it still casts a readable shadow back down onto the floor for us to see.
To monitor those shadows without bogging down the main system, SSR uses a dedicated hardware diagnostic scanner. This thing sweeps the entire global state matrix every 42.24 nanoseconds. It is insanely fast. It's looking for a vanishing determinant, which is a mathematical value of exactly 0, indicating a matrix collapse or a hidden infinity. This means your computer can literally catch and isolate a crash before it even gets the chance to manifest in the execution core.
And the debugging process at the hardware level is just beautifully illustrated by the Galois mirror core. Picture a primary processor physically bound to its phase-inverted twin. Every single operation in the main core instantly reflects in the mirror. Safe, healthy code perfectly cancels out into a totally flat 0 line. But those infinite loops? Since they lack associativity, they can't perfectly cancel. They end up sticking out as these unmissable jagged spikes that the diagnostic camera flags instantly. We're talking literal zero overhead debugging. Just incredible.
Now part 4. The p-adic fractal matrix. With all that chaos isolated and flagged, SSR doesn't stop there. It actually restructures the logic itself. It replaces standard binary bits with entirely new geometric structures. When you compare standard binary logic, you see base 2 bits and sequential pointer chasing, which really eats up time. But SSR trades all of that for multi-prime p-adic sequences. So instead of fetching data line by line, SSR fires off simultaneous optical broadcasts that manipulate the entire geometric lattice all at once. It's basically the difference between blindly walking through a maze and looking at the whole maze from above to instantly spot the exit.
The secret sauce making this work is non-Archimedean math. Think of p-adic distance kind of like a fractal Russian nesting doll. In this space, every point inside a circle is its center. Because of that, infinite loops don't expand outward to chew up your RAM and freeze everything. Instead, the geometry naturally forces them to collapse inward, shrinking all the way down to a totally harmless, static, geometric point.
Once it's collapsed to a point, the system has to fix the broken code, right? Enter the Adelic resolution operator and its Teichmuller lift. You can think of this mechanism like a high-end AI image upscaler, but for broken logic. It intercepts that collapsed packet, upscales it to high-precision Paddock integers, logically fills in any missing details, flattens out the rough edges, and then seamlessly drops the patched code right back into the execution matrix. You'd never even notice a hiccup.
So, on to part 5. Building computers with light. A revolutionary math theory obviously needs a revolutionary physical chassis to run on. You definitely can't run extra-dimensional geometry on standard copper wires. Check out how the physical implementation actually works. The hardware literally grows to match the software through a process called directed self-assembly. The physical width of the microscopic trenches in the chip architecture explicitly dictates the exact prime base of the mathematical matrix, like prime number 3 or 5. The hardware and software become physically and mathematically identical, and it's all built on a silicon-on-sapphire substrate, which is absolutely crucial.
Why? Because the data here is entirely optical. Silicon photonics actually turn color into a literal address. Micro-ring modulators encode those Paddock coordinates into light via the plasma dispersion effect. Basically, you're firing data off at the speed of light at frequencies well over 110 gigahertz. And thanks to that sapphire base layer we just mentioned, there is zero substrate leakage. The light stays perfectly contained and routes entirely passively.
All right, bringing it all together in part 6, the zero-friction future. Let's zoom out and look at the real-world impact of migrating our global computing infrastructure to this optical, Paddock architecture.
Because we're operating mathematically on a smooth genus 8 algebraic curve, data isn't being physically brute-forced through resistant wires anymore. Instead, the entire matrix is instantly mathematically rotated. This specific multi-hold curve geometry provides exactly 336 independent zero-friction routing lanes. That translates to massive, instantaneous parallel processing without generating any of the physical heat you get from electron friction.
So, what does this mean for our energy grid? By turning those chaotic chronological loops into static, idling coordinates and swapping copper for passive light routing, the thermodynamics just drop right off a cliff. To put it in perspective, an at-scale SSR facility requires a tiny fraction of normal cooling and compute power. We are talking about total power consumption dropping from a massive 157 megawatts down to just 13.2 megawatts. That is a jaw-dropping 91.6% savings in energy. It's a total game changer. And the security implications? Equally massive. Because p-adic memory balls are perfectly disjoint, meaning they never ever overlap, malware physically cannot find memory holes to exploit. The coordinates literally don't exist in the malware's metric system. It'd be like trying to find a street address in a totally different dimension. Plus, by lifting this lattice into the geometric Adel ring, the system strips data of linear periodicity, which completely blinds quantum computing threats like Shor's algorithm. It gives you out-of-the-box quantum immunity.
All of this culminates in naturally solving perhaps the most famous unsolvable riddle in computer science, the halting problem. By translating chronological execution into this self-correcting p-adic geometry where all those chaotic loops are safely routed to Adelic sinks, the SSR system physically bypasses the halting problem altogether. It simply doesn't need to guess if a program will stop. The geometry itself enforces structural stability no matter what happens.
Which leaves us with this final thought for our explainer today. We've just seen how stepping completely outside the standard rules of math fundamentally fixes the core flaws of computing. If infinite loops can just be folded away into extra-dimensional geometry, what other impossible computing problems are just sitting there waiting for a change of perspective? I highly encourage you to dig deeper into p-adic computing. It very well might be the blueprint for the next century of innovation.